Hi there. I'm the producer for Inside UVA, and I'm very excited to share a special interview with UVA alumnus and director of the National Institutes of Health, Francis Collins. I was able to join the team at the NIH when we recorded this episode last week. And I can tell you, it's a conversation you don't want to miss. Dr. Collins talks about his first research experience here at UVA as an undergraduate, his years leading the Human Genome Project, and how his scientific pursuits nudged him to belief in God. Plus, you'll hear a very unique musical performance of a very special song. I hope you enjoy this episode, and if you do, I hope you'll check out the links in the description below, where you can subscribe to Who's in STEM, a new podcast from the STEM advisor to the provost at UVA.
Welcome to Who's in STEM. I'm Ken Ono, your host and the STEM advisor to the provost and the Marvin Rosenblum Professor of Mathematics at the University of Virginia. On Who's in STEM, our goal is to evoke flights of imagination and wonder by showcasing the cornucopia of all that is STEM at UVA, the marvelous world of UVA science, technology, engineering, and mathematics. Science usually advances on the work of thousands, over generations, fine-tuning and extending the scope of understanding. But from time to time, creative fireballs and genuine visionaries burst onto the scene, propelling human thought forward. Think Isaac Newton. Think Marie Curie. Think Albert Einstein. Now, that introduction might embarrass today's guest, Dr. Francis Collins, because he is one of these figures. His research, which isolated the genes that cause Huntington's disease and cystic fibrosis, ultimately led him to direct one of the most audacious projects in the annals of science. And this is not hyperbole. The Human Genome Project. Its object, to divine and to uncover mankind's biological blueprint. Begun in 1990 and completed in 2003, this monumental feat has led to countless medical discoveries and therapies. But first, let's celebrate Who's Making Discoveries. As a spin on March Madness, a UVA health discovery has advanced to the Elite Eight in Stat Madness, an online tournament that crowns a significant biomedical achievement. The UVA discovery competing for the title is from the John Lukens lab. They've uncovered a molecule called a kinase that's responsible for orchestrating immune responses in Alzheimer's and multiple sclerosis. This finding sheds light on the toxic buildup of plaque in the brain that causes memory loss. A team of graduate students in UVA Engineering and the Darden School of Business have advanced to the national round of the American-made Energy Tech Competition. This is sponsored by the U.S. Department of Energy. They propose a plan for recycling lithium-ion batteries based on redox targeting technology. The team estimates that the market value of their plan, if extended through the year 2031, based on reuse of materials and reduced reliance on foreign suppliers, is almost $2 trillion. Generative artificial intelligence, AI, spin in the air, such as ChatGPT. This AI presents opportunities as well as worrisome challenges to teaching and learning. And UVA's provost and, well, my boss, Ian Balcom, has assembled a task force led by Bree Gertler that will study and then make recommendations to the university. As a first step, the task force will convene town halls where faculty, students, and staff will be invited to share their thoughts. And that's Who's Making Discoveries. In addition to being a world-renowned scientist, a recipient of the Presidential Medal of Freedom and the National Medal of Science, Dr. Francis Collins has led the National Institutes of Health for over a decade, including through much of the COVID-19 pandemic. He has also served as the science advisor to the President of the United States. Thank you for joining us, Dr. Collins.
I'm delighted to be with you and talk about my alma mater, the University of Virginia.
Wonderful. Dr. Collins, or Francis, if I may.
Please call me Francis.
I have to know, how did you first become interested in science?
I was homeschooled till the 6th grade by my mom and dad in the Shenandoah Valley of Virginia, growing up on a small farm. But by the time I got to the 6th grade, my mother decided it was time for her boys to go to public school. And it was a 10th grade chemistry teacher named John House. I hadn't really appreciated until then that this was a detective story. That's what science is. You kind of figure things out by following clues, and you do experiments, and you learn things about how the universe works that nobody knew before. Hey, I want to do that too. And he was a chemistry teacher, so I figured, okay, I should be a chemist.
Wow. So, Francis, you graduated from UVA in 1970. What are your fondest memories of your college years at UVA?
So I got there at age 16, partly because I had gotten this early start from being homeschooled. But I was totally jazzed about chemistry.
You said 16? You started college at 16?
I did.
Wow.
I tried not to let anybody know that because I was ready to blend in, which I hadn't been able to do so well in high school. So I was excited about science, and I knew I wanted to be a chemistry major. And so that's exactly what I stuck to. For my 4 years, I took every course in chemistry that there was, and most of the ones in physics, and a lot of the ones in math. And I was fortunate as a senior to sign up to do independent research. And my research advisor, who had just arrived that year, I was his first student, was Dr. Carl Trindle. Carl Trindle.
Famous Trindle.
The famous Trindle. Yeah. He wasn't famous then. He was like this new assistant professor trying to figure out how to do research with these undergraduates around who were pretty green. But he took me on, and he taught me things about how to apply computational methods to chemical reactions, the famous Woodward-Hoffman rules, and how they could actually be coded. And I was totally jazzed about that. And that was my undergraduate experience, my first publication, Collins and Trindle.
Wow. So for the listeners, this chemistry professor, he's a legend. And so it's amazing for me to hear you and learn that you were his first student. That's great.
I was, and we stayed in touch, right up until the present time, as he served as the principal of Brown College, living there in that Monroe Hill house where I would occasionally drop in and meet with his students. Just a wonderful mentor, role model for me.
Wow. So now that you've been director of NIH, I have to ask, what was the path? How did you go from chemistry to the world of genomics?
It was very nonlinear, this pathway. I had ignored biology completely during high school and college because it just seemed messy. I liked the elegance, the simplicity of chemistry and physics, and life just seemed way too complicated. And I almost had the sense maybe there isn't any rationale to how life works. And I discovered as a second-year graduate student at Yale, trying to get my PhD in quantum mechanics, that I'd been wrong about this. And there were people in the chemistry department studying this molecule called DNA. And it was a really fascinating information molecule that seemed to be calling to me, saying, hey, maybe you actually would want to work on this. It was a struggle then, because I was already well on the path, to be a university professor of chemistry, and to change course at that point and to take on what turned out to be many years of training by going to medical school and becoming a physician was a big decision, but it was the right decision. I came to Michigan as an assistant professor after doing all that medical training and learning something about how to do research in molecular biology. And the big project I started on, which everybody said is probably foolhardy because it's never going to work, is to find the actual specific misspelling in the genome that causes cystic fibrosis. We knew that was an inherited disease, inherited in a recessive fashion, but we had no idea what the gene would normally do. We just knew there must be something wrong there. So it meant applying tools that were very clunky to try to narrow this down to some part of the genome, ultimately on chromosome 7, and then using a technique I invented called chromosome jumping, try to travel around in that uncharted territory, because the genome was uncharted in the 1980s, and try to find what might be as subtle as one letter that was misspelled. Turned out to be 3 letters. just a CTT that was missing in an exon of a gene that nobody had ever paid attention to or had any idea what it did. That is the common cause of cystic fibrosis. And that took quite a few years, and a lot of graduate students and postdocs. It was very painful because you'd go down all these blind alleys and realize you had missed the boat and have to start over. And that was a big motivation, frankly, for saying, if we're going to do this for all those thousands of diseases we want to sort out, we have to have a reference genome. We have to have something to work with. We can't be in the dark all the time.
And hence the Human Genome Project. So, in simple terms, what is the Human Genome Project?
Well, first of all, what's the human genome? It's basically the DNA instruction book for our species. It's in that strange language with its four-letter alphabet, A, C, G, and T. And it turns out that the whole instruction book is 3 billion of those letters long, which is a lot, but it still is pretty astounding to contemplate that that's enough. You get 3 billion from mom and 3 billion from dad, and you start out as one cell. And that instruction book has to be sufficient to take you forward to what we now are, very complicated organisms that are capable of amazing things, including a brain that in many ways is the most complicated structure in the known universe. All that has to be encoded within that finite amount of information. And the Genome Project was just bold enough to say, let's read it for the first time. Let's read the whole thing.
Right. So, as I understand it, the overlap between the human genome and the genome of other mammals is really quite significant. So, our differentiation between you and me and between any two people on planet Earth is a very small subset of that 2%.
About 0.1% difference between you and me, and that would be true if I was talking to anybody else who lives on planet Earth. We are a very young species, and genomics gives us, if we needed more evidence, the evidence that we are all related. We're all part of one family. And anybody who is trying to use genetics as an argument for racism should realize that that doesn't work anymore. The science will not support it.
So going back to your work on the genome, the Human Genome Project, how did you know you were going to succeed?
Well, when I got called to come to NIH to lead the Genome Project, I was pretty worried about that. In fact, I said no the first time. It seemed like this was a fool's errand. It was probably not going to be possible to read out these 3 billion letters in the 15-year timetable that had been projected. And
you beat it by 2 years.
We beat it by 2 years eventually, thanks to what was an amazing opportunity to recruit the best and brightest biologists, computer scientists, automation experts, technology developers who all said, you know, we're only going to do this once in all of human history. I want to be part of it. So ultimately, the Genome Project, although I had the privilege of leading this was 2,400 scientists in 6 countries working together 24/7 to try to put all of the pieces together to read this out for the first time. And that was an amazing team. And nobody worried too much about who was going to get the credit. And we gave all the data away every 24 hours so people could start using it.
Oh, that's fantastic. So the Human Genome Project per se was completed in 2003, but there must be a post-genome project. Have we entered that era?
People make jokes about, okay, we just announced we finished the Human Genome Project again. Because what we did in 2003 was a fantastic sort of result. It was what we hoped we would have. But there were still messy parts of the genome, like the centromeres that are made up of these anonymous, sort of hard-to-read repeats. We now finally, just this year, have truly the complete genome that includes all of those messy parts. They don't seem to have a lot of genes in them, but we still want to know that they're there.
Right.
But more than that, we really want to understand how the genome works. Just staring at 3 billion A, C, G, and T doesn't give you a lot of insight. So we need more experimental data to say, okay, where are the genes, the part that code for protein? We're pretty good at that. And then what about the rest of it, the 98% that doesn't code for protein? That's the regulatory stuff. And that's incredibly interesting and, frankly, incredibly complicated. This is what you call epigenomics. And a lot of labs, including mine across the way here in Building 50 at the NIH, is working really hard to try to understand how the epigenome guides the expression of those protein coding genes so that your liver cell is doing very different things than your brain cell or your bone marrow cell, but they all have the same genome. So something very amazing is going on there in terms of regulation.
That's right. I want to circle back to the success of let's say, the first phase of the Human Genome Project. So despite the fact that the work is ongoing and perhaps will be ongoing for the foreseeable future, can you share with us some examples of real successes, some therapies, some evidence that this monumental feat has improved the human condition?
Well, there are a lot, and there are more every day. There is this first law of technology that says a truly significant advance in science will always have its consequences overestimated in the short run and underestimated in the long run. And I think that's happened with the genome. There were people saying, the day after we had the 2003 announcement, okay, when you go to your doctor tomorrow, it's all going to be different. No, it takes.
and that's before the day of the internet. It's before Google.
Yeah, exactly. But now see where we are. Let's say cancer, for instance. Anybody who has a new diagnosis of cancer today ought to have that cancer sequence, that is, read out all the letters of the genome of those cancer cells and find out what is driving those good cells to go bad. Because cancer is a disease of the genome. It happens because of mutations that activate an oncogene or knock out a tumor suppressor gene. And you want to know that if you have a new cancer, because it's going to give you the best chance to pick on the very long menu of therapeutic interventions, what's the one that's right for your cancer. That is almost now standard of care, and it would never have happened without genomics to get you there. Take what happens in the newborn nursery. I'm a physician who trained in medical genetics. I would go to the newborn nursery, and there would always be kids there who clearly were not thriving, sometimes actually quite worrisome, having seizures, maybe having some kind of congenital malformation. What is going on there, and what should we do to help? Oftentimes, those dilemmas would go on for months without an answer. Now you can sequence that baby's genome, most recently in 24 hours, that's been done at least once, and get the answer and know what the diagnosis is and what to do about it. And oftentimes, it makes a huge difference in the care.
And possibly even before birth, right?
Indeed, and of course, lots of that also happening. Look at infectious disease. All of the things we learned about COVID and all of the things we learned about those new variants, whether it was Beta or Delta or Omicron,
right.
all coming about because of sequencing, in that case of the viral genome, a lot smaller than the human, but the same technology, making it possible to get those answers very quickly. It's had all those kinds of spin-offs.
Right, in a matter of days, right?
Yeah.
You watch the news, 2 weeks later, there's a new Greek letter variant.
And you want to know that, because it's going to have a
that.
lot of effect on what public health recommendations need to change when you see a new variant coming at you.
Right. So I kind of want to shift gears here. There are several facets of your professional life and career that we could talk about, and one of them speaks to me. So in addition to your leadership and research, you're known for your views about faith and science. And I have to tell you, after reading one of your books, I was myself baptized in my early 40s. It was really a transformational experience to me, and I want to share that with you. But where does that come from? As a theoretical mathematician in my work, I want to understand both the abstract world of numbers and, of course, our shared, experienced physical world. And it seems that each time mathematicians and scientists answer a difficult question, they're thinking they're making a step towards complete understanding. But we typically actually find that this new knowledge instead reveals new and often more difficult questions, an infinite and impossibly long path. Indeed, we've already touched on this. Chemistry and physics didn't end with the discovery of the atom. Biology, as we've discussed, certainly didn't end with the discovery of DNA. These historic discoveries were just mere beginnings. And this is the way of science. A humbling process that reinforces the complexity and the wonder of life that is the world around us. So I like at this point to bring up one of my heroes in mathematics, an Indian mathematician by the name of Srinivasa Ramanujan, who lived over 100 years ago, and he believed that his mathematical ideas were sent to him as gifts from a Hindu goddess. And he famously wrote that an equation has no meaning to him unless it expresses a thought of God. And this reminds me of something that you wrote, that the God of the Bible is also the God of the genome. God can be worshipped in the cathedral as well as in the laboratory. And I would like to hear your take on not just that quote, but I really want you to expound on your personal experience and how you came to to write your book and speak about these things.
Glad to. I did not grow up in a faith environment, nor was I particularly attracted to conversations about faith. By the time I was a graduate student studying quantum mechanics, I was a committed materialist and an atheist. And then I went to medical school, and I had to face, at the bedside of good, honorable North Carolina people who were facing death, that I didn't have any really good answers to questions like, why am I here? What's the meaning of life? What happens after you die? Why is there something instead of nothing anyway? And I realized science, which I had so attached myself to, was not giving me satisfying answers to those questions. And in a certain way, I think I realized I had impoverished my ability to be able to seek truth by limiting that to the kind of truth that only science could discover. And that didn't feel like a good thing. I figured I'd better learn more about this because I figured there were some pretty thoughtful people who had not checked their brain at the door, but who ended up believing in God. And I wanted to understand why and how that was possible. And after 2 years, assisted by some mentors who helped walk me through my blasphemous questions.
Scientists?
Yeah. A pastor who lived down the street from me, C.S. Lewis, the Oxford scholar who had traveled the same path that I found I was on, from atheism to faith, and anticipated my objections almost before I had quite formulated them, was a wonderful guide to this. And ultimately, over that 2-year period, realized that for me, atheism had to be rejected. It was the least rational of the choices. It was the assertion of a universal negative, which scientists aren't supposed to make. Agnosticism felt kind of like a cop-out, like, okay, I just don't want to think about it. At least that's what I felt like I was doing when I went there. I had to understand, is there actually a case to be made for belief? And to my surprise, a lot of that turned out to come from science. The fact that there was a Big Bang and we can't explain what came before that singularity, which cries out for a creator who can't be limited in space and time. Oh my. The fact that, our universe follows certain laws. You're a mathematician.
Symmetry is everywhere.
Those laws, we know they're right because they're simple and beautiful. Why should that be? Why should matter and energy, pay attention to things like Maxwell's equations? And yet there it is. And why is it that the universe is so fine-tuned? That is something I think very few people have got their heads around, that if those constants that are the part of gravity, the strong and weak nuclear force, the speed of light, if they were off, any one of them, by even a part in a billion, the whole thing wouldn't work. You would never end up with anything interesting in the universe. Maybe some particles flying apart, but nothing more than that. Somebody set the dials. And that takes me pretty quickly then to the idea that there has to be an intelligence behind the universe. The challenge then was, is it an intelligence that cares about me? Or is this, a creator who kind of went off and did something else after this? And here's where the moral law really began to speak to me. Why is it that all of the examples we know of down through history of human communities have had this sense that there's something called good and there's something called evil, and we should try to do what's good, and knowing that we will generally fail, but we still understand that's important and we strive for that. Where does that come from? Some will say that's just evolution. Well, it doesn't work so well. When you do something truly sacrificial for somebody you don't even know that might threaten your ability to reproduce, you're not following evolution's mandates. And yet we admire that. We think that is true human nobility. Where is that coming from? That felt like a signpost, not to a deist kind of God, but to a theist God who cares about people, cares about me.
Francis, that was awesome. Well, we do have to begin wrapping up here. Are there any bits of wisdom and encouragement that you could offer our students on grounds who are preparing for final exams?
Be of good cheer. Well, first I would say you're really lucky, the students on the grounds, to be at this remarkable university with its long traditions of really caring about truth and training up students in all kinds of different disciplines to become leaders. My time in Charlottesville at UVA was truly formative and I wish that for all of you as well. And I think given the experiences that are possible there, you're really fortunate to be at one of our world's finest locations of higher learning. I would also say, if you're interested in STEM, and we are here to talk about STEM, there could hardly be a more exciting time right now to be involved in science, technology, engineering, and math, because there is, after all, an exponential curve that's underway right now in terms of the ability to discover new things. Certainly in the field I know best, medical research, we are in an amazing time. We're curing sickle cell disease, that first molecular disease, using things like CRISPR gene editing, which just got invented 10 years ago and is now saving people's lives. We are finding ways to cure people with cancer using the immune system, immunotherapy, in a way that I think is beyond expectations that most of us would have thought possible. We're figuring out how the brain works in this amazing combination of engineers, computational experts, neuroscientists working together to see how do those 86 billion neurons actually do this amazing, complicated things that they do using circuits that we're just beginning to understand. You want to be part of that.
Right.
This is the time.
Right. Well, that's what Who's in STEM is about. It's our ability to share the discoveries that happen on ground. So, hear. One last thing, Francis. My friend, President Ryan, tells me that you're a real live rock star, a guitar hero. And I actually see right here you've got this lovely guitar which has a double helix on the fretboard.
I was able to design this guitar. When I stepped down as leading the Genome Project, people who'd worked on it took up a collection and decided I needed a new guitar. So this was built in Stanton, Virginia, my hometown, by a wonderful luthier called Husson Dalton, and I got to design this double helix in mother of pearl on the fretboard. The wood on the top is Adirondack spruce from the Blue Ridge Mountains. And it does have a name. And of course, I'm a guy who thinks a lot about DNA, so some people might have said you should call it Watson or you should call it Crick. No. Remember, Watson and Crick figured out the DNA double helix, but they did it by looking at data without permission of the woman who'd actually done the science with X-ray crystallography to figure out the pattern that led to the double helix. And that was Rosalind Franklin. So this guitar is Rosalind.
Love it. So, do you take requests?
Depends on what they are.
Okay, well, Francis, you've got to sing UVA's alma mater, the good old song.
I was afraid it was going to be hip hop. Okay, I think I can make this work. And I got to tell you, it's been a long time since I sang this song, and I'm not sure when I was an undergraduate, off in the physics lab late at night instead of going to the games, I missed a few of those. But let's see if I can pull it off here. The good old song of Wahoo-Wah, we'll sing it o'er and o'er. It cheers our hearts and warms our blood to hear them shout and roar. We come from old Virginia, where all is bright and gay. Let's all join hands and give a yell for dear old UVA. Wahoo-Wah, Wahoo-Wah, Univ, Virginia. Hooray, ray, hooray, ray, 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 UVA!
Everybody here, that's awesome. So Francis, thank you very much. You are an extraordinary example of President Ryan's vision for UVA to be great and good in all that we do, and you make us all very proud, and you're a gift to the United States of America.
Thanks. It's been great to chat with you, and wahoo-wah.
So I'm Ken Ono, STEM advisor to the Provost and the Marvin Rosenblum Professor of Mathematics, and you've been listening to Who's in STEM.
For more conversations like this one, please subscribe to Who's in STEM. There's a link in the description below. The podcast has already covered new phone apps that can help track mental health wellness, diabetes technology, and conducting research in Antarctica. It's a great way to keep up with all the innovation happening right here at UVA. A new episode of Inside UVA will be back in your feed next week.